All right, let's talk about conservation laws. So suppose we have a quantity Q, and Q is the density of something. So it could be the mass density, in which case we would think of Q as rho. Q might be the momentum per unit volume. Then in which case Q would be a vector, right? Because momentum is a vector. It could be the energy content, the internal energy of a fluid parcel. That could be Q per unit volume, the specific internal energy. It could be the amount of salt per unit volume. So we have this quantity Q, and the amount of Q in a given volume. So if I pick some volume, it could be an arbitrary volume, right? Some volume V, and it has a boundary partial V. So this is the boundary of the surface, and this is the volume. Then the total amount of Q inside this volume is going to be obtained by integrating dV over the volume, right? So if I do the volume integral of Q, I just don't need all these triple integrals, it's a volume integral. Just put one integral. So that's going to be the total amount. Now if I want to think about the rate of change of this quantity, then I can take the partial derivative with respect to t, right? And this will tell me the rate at which the amount of the stuff Q inside the volume is changing. And there's going to be two ways in which it can change. One, there could be sources on the inside, right? Internal sources or sink. For example, if Q was radiocarbon, then there would be a loss of radiocarbon inside the volume because of radioactive decay. And so one way in which we can think of the loss, or sorry, we can think of the rate of change is going to be equal to the volume integral of any sources or sinks inside the domain. So that's one way you can change. Another way in which the total amount of stuff can change might be because there are fluxes coming in through the surface, right? So we could also, if we think of the outward flux, so the negative of the outward flux will be the inward flux, so it will be the surface integral dV, over dV, the boundary, of some flux J through the surface, right? So J here, so J is the flux of Q. So if we integrate J over the surface, we will get the total amount of stuff. If J is the stuff leaving, then minus that will be the stuff entering. And that will give us the time rate of change of Q. And the next thing we're going to do is we're going to use Gauss's law to convert this boundary integral of the outward flux in terms of the divergence inside the volume. So we can rewrite like this using Gauss's law. So this part we keep the same, S, V, dV. And then this one will become minus the integral over the volume now of the divergence of J, dV. Right, so this is through Gauss's law. So it allows us to convert the surface integral into the volume integral. And now I could bring everything onto one side, and what I'll have, I can bring everything onto one side. But another thing I want to do is I'm going to take the volume, V, to be fixed in space. So it's a fixed volume, it doesn't change with time. So if V is a fixed volume, fixed, independent of t. So if it's independent of t, then I can take the time derivative inside the integral. So I'm left with d by dt of q. And if I bring these terms over on this side, I'll have plus from this term, div dot j minus s. Or maybe I'll keep the s on the other side. I'll keep the s on this side, equals the volume integral of s dv. And on this side I need a dv. All right, so this is my conservation law expressed as an integral for some volume v. Now the volume v here was just some arbitrary volume. I can pick it to be anything. And so since it could be anything, the only way this relationship can be true is if the integrand vanishes everywhere, right? If it wasn't, so suppose that you had one little part of your volume where the integrand, the part I'm integrating, let me keep it all on one side, minus, it's easier to think about, minus equals 0, right? So I claim that the only way this can be true for any volume V is if the integrand vanishes. And the way to think about it is suppose that the integrand didn't vanish in one little part of the volume V. So there's a little part, and we can pick that little part to be as small as we want, and so we can pick it such that this will have the same sign everywhere. And so if this is all positive in that little volume, then there's no way the integral will be 0. So that means that any small volume, the integrand has to be 0, otherwise we'll get a contradiction. And so this implies the following. The integrand has to be 0 everywhere. So we get d by dt of q plus div dot j is equal to s. And this is my conservation law. So this is a general conservation law written for a continuum. And so we're going to use this form of this equation for all kinds of things, for example, for mass, for momentum, internal energy, for salt. We're going to use an equation of this form. The only thing that's going to change is, of course, the sources and sinks are going to be different for different quantities, and the flux of the quantity is going to be different for different things. Clearly, if we're talking about density, then this will be the flux of mass. But if we're talking about momentum, then this will be the flux of a vector, right? So if you think of it, you'll have two directions now. You'll have the direction in which things are moving, and then since the quantity you're transporting is a vector, you'll have some complicated object over here, namely the stress tensor for the momentum. But let's do a simple example first. Let's do mass. So for example, suppose Q is just the density, right? Then the J in that case, J, is going to be the flux of mass, right? And that's going to be the velocity times the mass, right? The mass, V is the speed of the mass. And if we do the velocity per unit volume, or sorry, the flux of mass per unit volume, right? We put flux of mass per unit volume, delta V, is the same thing as V times rho. So this will be the J in this case for the continuity. Now, what will be the source and sinks for mass? Well, since mass is neither created nor destroyed, I'm assured that S will be 0 in that case. So then this is true, and S equals 0. So what my equation will become will be d rho dt plus div dot v rho equals 0. And this is 0. This is the continuity equation for a fluid, so it expresses the idea of the conservation of mass. So this is known as the continuity equation. Continuity equation, and it expresses the conservation of mass. Conservation of mass. Let's write down what this expression looks like now in Cartesian coordinates. So the continuity equation in Cartesian coordinates. So in Cartesian coordinates, then the continuity equation will be d rho dt plus d by dx. And let's write down the components of the velocity v. And I'm going to introduce this time, and I will use this from now on. There'll be three components, right? Vx, Vy, and Vz. And in oceanography, we almost always express these components as U, V, and W. In other words, W is the vertical velocity, positive upwards. V is the eastward velocity, no, the northward velocity, and U is the eastward. So east, north, upward. And we imagine that at each point we have a little Cartesian coordinates where Z points upwards, Y points northwards, and X points eastward. So this will become rho U plus d by dy rho V plus d by dz rho W equals 0. So this is the continuity equation in Cartesian coordinates. And we can rewrite it one more time. You can use the product rule to expand these terms. And what we're left with is d rho dt plus u times d rho dx, right? And then I'll be left with a plus rho d by dx of u from the first term. From the second term, plus v d rho dy plus dv dy. And then the last one, plus w d rho dz plus dw dz equals 0. So I've broken it up into two parts, and I can now rewrite it one more time as d rho dt plus. So now here I can think of the dot product, right, of the vector v, the velocity vector, dotted with the gradient of the density. So this looks like v, the vector v, dotted with the gradient of rho. Remember, the gradient of rho is d rho dx, the first component, d rho dy, and d rho dz. And then the last term will be plus rho times, and this is just the divergence of the velocity field, div dot u. And this is also the continuity equation. And you will recognize after you've done the homework, this week's homework, that the first part is the material derivative, or the derivative of the density following the flow, right? That's the time rate of change of the mass per unit volume as you move along with the fluid parcel as it moves. And so sometimes this first part, which is called the material derivative, will be expressed this way. Either written in this way, the first part here will be d, we'll use the big d by dt, the upright d, rho dt plus rho div dot u, v, I should have written v here, div dot v equals 0, and where d by dt of rho, and it's sometimes written at capital D rho dt, is equal to d rho dt plus v dot grad rho, where this is the velocity of the fluid. All right, so much for conservation equations.